Hello again. We will be covering acid-base neutralization in this video. So once again, I'm going to point out the fact that we're going to remember that an acid donates a hydrogen and a base accepts a hydrogen. And for these problems, the formation of a water molecule or an H2O is the driving force for these problems. So the first thing we want to do is to create our water molecule, and then we're going to then have a salt that is created. So when we get to the point of combining our compound or our different elements to create that salt compound, please note the cation and the anion in your problem, because the placement of those particular items in the compound can make your answer either wrong or right. So remember, our cations are in the first location and they are going to be positively charged. And then we have our anions that are in our secondary position that are going to be negatively charged. Also, we need to remember that we do have polyatomic cations or polyatomic anions. All right, so let's take a stab at this first problem. Here we have HCl and NaOH. So we need to first form our water molecule. So we know we need 2 hydrogens and 1 oxygen. Well, looking here at our problem, we know that we're going to form a water in the product side. So let's go ahead and place that there. And once we do that, we're going to come back and look at our reactant side. So we formed our water, but what did we form that water from? I have a hydrogen here, I have an oxygen here, and I have a second hydrogen. So there is 2 hydrogens for my H2 and 1 oxygen for my O. So now we are left with chlorine and sodium. And once again, I will mention we need to make sure that we have our cation first and our anion second. So if we look here at our 2 elements, we know that sodium is our positively charged cation. So we're going to go ahead, remembering our rules of naming and writing compounds. We're going to start with sodium. And then we are then going to utilize our chlorine. So we now have sodium chloride. But let's take this one step further, okay? Let's go ahead and label which is an acid and which is a base. So remember, we had a donator of hydrogen. So who donated my hydrogen for my water? Okay, so we have here our HCl is going to be our acid. We have NaOH, which is our base. And then we have our NaCl is our salt. And then there is our water, our driving force. Our driving force for our whole compound. All right, so now let's take a look, and we're going to go a little deeper because they're not always that straightforward. And that is why I mentioned to you the rules of naming. Because here we have another chemical equation, HCl plus CaOH2. So there's times when we end up having subscripts in some of our compounds. So for the purposes of balancing, we would typically use that 2. But for us to make our compounds to complete our chemical equation here, we're going to have to do a few things. So we mentioned in our naming video the crisscross method. We know here that hydrogen and chlorine both have a +1 or a -1 charge. So there's no need to do any changing with that. So we know we're going to end up with 1 hydrogen. We're going to have 1 chlorine. But let's take a look here. We have CaOH2. If you will reference your common anion, cation, and polyatomic sheet, you'll notice that we will need to use the lasso method in reverse here. Because in fact, we don't have 2 of our hydroxides. This 2 is actually from the rules of naming for the charge for this calcium. Likewise, whatever charge would typically be here as a subscript for calcium would then return to its original position with our hydroxide. So we have here a Ca2+, because once we reverse lasso, we know we have calcium with a +2 charge. And then we have here our OH with a negative charge. Okay, fill in those on our other items as well. Now let's take these items and let's go ahead and make our balanced equation for our acid-base neutralization. So this is where we see all of our concepts come together. So we know that the formation of water or an H2O molecule is the driving force. So we're going to go ahead and create our H2O because we know the driving force is the first thing I think about. So I can go ahead and get rid of this OH here and this hydrogen here. So now we're left with a calcium, which is a Ca2+, and we need to combine it with chlorine. All right. So how would we do that? Now we're going to go back to those original rules of naming and do that lasso right back. So now we're going to take that 2+2 charge and send it to be associated with the subscript for chlorine. We're going to take that -1 and that charge is now going to go there. So let's go ahead and combine this cation and this anion. So we know we're going to have H2O plus CaCl2. But we want to make sure that our equation is balanced completely before we walk away. So here we should have, if we go through our rules of making sure our equation is balanced. So let's go ahead and dig into that. Okay, so here we're going to make our list. I have hydrogen, chlorine, calcium, and oxygen. I'm going to do the same thing for the other side, leaving that shopping list in the exact same order. And let's count these up. I have 1, 2, 3 hydrogens. I have 1 chlorine, 1 calcium, and 2 oxygens. Let's take a look here. I have 2 hydrogens, 2 chlorines, 1 calcium, and 1 oxygen. So we have a few things that are out of number, okay? So we're going to leave our hydrogens and oxygens last, but let's go ahead and take a look at chlorine. I have 1 on my reactant side and 2 on my product side. So how would I change that chlorine to 2? I would use my least common multiple. And please remember that once you place a number in the mole position, you can change that. The only thing we cannot change are subscripts. Those cannot be changed. So we're going to go ahead and place a 2 in front of this first compound. And remember to update our shopping list that's associated with this problem. So now instead of 3 hydrogens, I have 2, 3, 4, because this 2 is distributed into that equation. It was only lassoed in reverse for us to get the proper compound for the other side of the equation. All right, so now let's adjust our chlorines. 2 distributed to that chlorine is now going to give us 2 chlorines. So if we take a look, we now need to get back into balance our hydrogens and our oxygens. And this is why the rule of leaving those second to last and last can be very beneficial, because typically hydrogen or oxygen is a diatomic element or compound. So you'll either see them appear in multiples of 2, or you'll see them paired together in water with a 2-to-1 ratio. So here we have 4 hydrogens on the reactant and 2 on the product for hydrogen. And we have 2 oxygens on our reactant and 1 on the product. So if we were to go ahead and adjust our hydrogens to get them equal, if we were to add a 2 in front of our water molecule, that would change my number of hydrogens from 2 to 4, because we now have 2 times this 2, which would give us 4. We also need to adjust our oxygen in that same problem because it is attached to this H2. So 2 times that oxygen there is going to give us 2. So now if we take a look, we have 4 hydrogen on each side. We have 2 chlorine on each side. We have a calcium 1-to-1 on each side, and then 2 oxygens on each side. So this acid-base neutralization problem has actually been completed. So please remember, the only reason we did a reverse lasso is so that we could get the proper compound in our product, and then we needed to go back through and balance that equation. All right, so I hope this was helpful, and once again, as always, happy studying, everybody.